Use sole tenant nodes to keep your VMs physically separated from VMs in other projects or to group your VMs together on the same host hardware. Hello and welcome everyone. In this video, we are going to look at how to create a virtual machine in Google Cloud using the web console. The console provides easy to follow steps to have a machine up in a few minutes. This video assumes that you have a Google account and you're able to log in into the console. In case you don't have a Google account, then see how to get to the console through the link in the description section. And without taking any more time, let's begin. Now, you can use either of these options. 1. On the homepage, under Resources widget, click on Compute Engine, and this will take you to the Compute Engine page. Option 2. You can use the search bar, and typing VM, then selecting VM instances will open the Compute Engine page as well. Option 3. Click on the list icon at the top left corner of the window, click or hover on Compute Engine, then select VM instances, and this will take you to the Compute Engine page. Now, for first time use, you will encounter a page just before this one that prompts you to enable the Compute Engine API. This is the API that allows you to create and run virtual machines on the Google Cloud. For this case, the API is already enabled. You should know that every resource that you create on Google Cloud has to exist within a project, which forms the basis for creating, enabling, and using all Google Cloud services, including managing APIs, enabling billing, adding or removing collaborators, and managing permissions for Google Cloud resources. For first-time use or a new account, Google Cloud will create a default project for you. Click on New Project, just in case you need to create your own, and specify the name of the project and organization if your account is tied to one. For this demo, I will use the default project, so I'm going to cancel out of this. Click on Create Instance, and either of these two options will work for you. And this will take you to the Create an Instance page. Now, here you're provided with 4 options on how to spin up the VM. You can spin up a VM from scratch, which is what you're going to do in this video. You can spin up a VM from an existing template. Basically, a template referred to as an instance template in Google Cloud lets you describe a VM instance. You can then create groups of identical instances based on the template. You're also provided with the option to spin up the VM from an existing machine image. A machine image is a resource that stores all the configuration and data from one or more disks required to create a virtual machine instance. And lastly, you're provided with the option to skip all the configuration hassle and deploy a ready-to-go solution. This option comes with preset configuration that spins up the VM and installs the required application as chosen from Marketplace. All these are subjects for another video. For this one, we are focusing on the first option, creating a VM from scratch. You will notice that you're provided with the cost and its breakdown, which I think is a great to show attribute at this point. But this is subject to this default config, so it will change as we proceed with the setup. Now, let's start by giving the VM a name. I'm calling this one Play VM. So, for instances where you are dealing with a group or fleet of VMs, labels help you to organize your project. You specify them as key value pairs to your resources. Use labels to indicate different environments, services, teams, and so on. For this instance, let's use service as the key and play as the value. Next, select where you want to host a virtual machine. And it's always best to choose a region closer to you or your customer for low latencies. So for this case, since I'm in Kenya, the closest region that GCP provides is Mumbai. You also have the option of getting specific and selecting a preferred zone, which is an isolated location within the region. A zone represents one or more data centers within the isolated location. So this means that it determines what computing resources are available and where your data is stored and used. Next, select the virtual machine's hardware sizing, and Google Cloud provides you 4 machine family options. Select general purpose for common workloads and scenarios where you need a balance between cost and flexibility. Go for compute optimized if your workload is compute intensive. Choose memory optimized for memory intensive workloads, and select the GPU for high performance computing and visualization workloads. For this demo, I'm sticking with the general purpose machine family. You're then provided with the options to choose compute power by selecting CPU series and machine type, which specifies vCPU against memory ratio. You can either use existing preset ratios or customize your own. You will notice that with each selection change, this cost calculator gives you a monthly estimate in real time. But for this demo, I will stick with the default E2 medium, which is the recommended minimum sizing for Windows image. Now, for cases where you need to get into the specifics of the platform within the chosen series, you're provided with the options to do that under CPU, platform, and GPU. Select the GPU platform, though the E2 series does not provide other options, but any of the other types do. Select the desired virtual CPU to core ratio. So, just to give you a quick one on this, on Compute Engine, each virtual CPU is implemented as a single hardware multi-thread, and two vCPUs share a physical CPU core by default. This option lets you manually set the value for the number of threads, that is, vCPUs per core. You might have some workloads with concerns such as performance, security, and licensing that might benefit from setting the number of threads per core to 1. And next, you're provided with the option to set the number of visible cores, which are the physical CPU cores in the underlying hardware that your VM consumes. Reducing the number of visible CPU cores reduces the number of available vCPUs. So, because our current predefined machine type only has one core, then we have only one option. Although, to best utilize this feature, you might need to consider using a custom machine type that provides the flexibility for more options. But for this demo, I don't need any of these options. I'm sticking with the E2 series. And essentially, the options remain the same for the other machine families. So, if the application on your VM will require a display device, but do not require the full power or cost of a GPU, you can configure your instances to use a virtual display device by selecting the Enable Display Device option. These devices allow you to run remote system management tools and remote desktop software that require a display device. And there is no cost to enable your instances with a virtual display device. The next option is Confidential VM Service. So, this service adds protection to your data in use by keeping memory of this VM encrypted with keys that Google doesn't have access to. Clicking on it will pop up a window informing you of the necessary settings that Compute Engine needs to update in order to make this VM compatible with this service. And this includes a change in the machine type and boot disk image. Though I don't need this for this demo, so I'm going to cancel out of it. Next, you're provided with the option to deploy a container to your VM instance by using a container optimized OS image. Clicking on Deploy Container will pop a side window for you to specify the container's configuration. Type in the container image name, and this has to be an actual name of a public image on any registry or a private image hosted on Google Container Registry. Select a restart policy to specify whether to restart the container on exit. The default option is always, and this means that the container will always be restarted in case it stops. Or you can choose to restart the container on failure or not to restart the container at all. But the default option is the preferred option. So again, by default, containers are not allowed to access any system devices, e.g. storage devices or network interfaces. Enabling this option will make the processes in this container equivalent to processes running as root on this VM instance. The next option is Allocate a Buffer for standard input, which does exactly what the name states. It keeps the standard input stream open, which is necessary for establishing an interactive shell in the container, and for the container to receive its standard input from a pipe. And this works along allocating a sudo tty option, which is necessary for establishing an interactive shell in the container. Next, specify your entry point command if you need to override the default entry point command from the container image. The entry point of a container image basically specifies what executable to run when the container starts. For example, here I wish to run Apache Server. You can also pass arguments to the container entry point command, and this will override the default arguments provided by the container image. For instance, here I would like to run Apache Server in the foreground. Be sure to enter each argument in a separate text box. Next, you are provided with the option to enter environment variables for use in the container in key value pairs. And again, you will need to enter each pair separately. The next option allows you to mount a directory or additional disks to the container. But before you do that, you will first need to attach the disk to the instance in the disk section, which we will cover in the coming steps. After that, you can then proceed to add the corresponding volume mount here. So, clicking on Add Volume will open up a set of parameters required for this setup, and you will need to specify the volume type, which can be directory, disk, or temporary file system. Specify the mount path, that is, the path in the container file system where the volume will be mounted. Then specify the path to the host or source directory. And lastly, specify whether to mount the directory in read-only or read-write mode. The options should be the same for the other volume types except for disk. you will need to specify the disk name and partition number, while for temporary file system, you will only need to specify the mount path. But since I do not intend to deploy a container to this VM instance, I'm going to cancel out of this. Now, a VM instance will always require a disk to boot from. The boot disk section allows you to select an image or snapshot to create a new boot disk, or you can attach an existing disk to this instance, that is if these defaults do not work for you. Clicking on change will side pop the boot disk configuration window where you are provided with the options to select a public image, a custom image from any project, a snapshot from the host project, an archive snapshot from the host project, or an existing disk within the host availability zone. Under public images, you're provided with options to select the desired operating system, and Windows Server is what we need for this demo. Select the version of the operating system. Here you're provided with some options, and Windows Server 2022 Data Center Edition is what I need for this demo. Choose the boot disk type and size. Now, for boot disk type, you will want to go with balanced persistent disks if you need SSDs that balance performance and cost. Choose extreme persistent disk if you need SSDs with consistently high performance for both random access workloads and bulk throughput, for example, high-end database workloads. Go for SSD persistent disk if you just need basic SSDs with no perks attached. And choose standard persistent disk if you need the regular hard disk drives. The advanced configuration tab will go deeper into the disk's configuration, and in most cases the defaults will suffice. But just in case, here you're provided with options to choose a deletion rule, so you can either keep the disk or delete it when deleting the virtual machine. You can also choose the encryption key management solution, and by default, Compute Engine encrypts all data at rest, so basically it handles and manages this encryption for you without any additional actions on your part. However, if you want to control and manage this encryption yourself, you can provide your own encryption keys using the next two options. The customer managed encryption key gives you control over more aspects of the lifecycle and management of your keys, such as you can protect your data using a key that meets specific locality or residency requirements, or you can automatically or manually rotate the keys used to protect your data. While the customer supplied encryption key option allows you to provide your own encryption keys, and Compute Engine uses your key to protect the Google generated keys used to encrypt and decrypt your data. You should note that Google does not store your keys on its servers and cannot access your protected data unless you provide the key. This also means that if you forget or lose your key, there is no way for Google to recover the key or to recover any data encrypted with the lost key. The next option allows you to use a snapshot schedule to regularly and automatically back up this disk. This is a recommended best practice for your Compute Engine workloads, and basically it's a resource policy that you can apply to one or more persistent disks. So the snapshot schedule needs to exist for you to attach it to this disk at this point. See the link on how to create one in the description section. And finally, you're provided with the option to give the disk a custom name. You can use this name to reference the disk for mounting, resizing, and so on from within the instance. By default, the disk name is based on the instance name. Click on select to settle on these options, and you will notice that there is a significant change on the monthly estimate. Now, your workloads will in most cases have the need to communicate with other Google Cloud resources. And for that, you should know that the authorization provided to applications hosted on a Compute Engine instance is limited by two separate configurations. 1. The roles granted to the attached service account, and 2. The access scopes that you set on the instance. Both of these configurations must allow access before the application running on the instance can access a resource. Now, a service account is a special kind of account used by an application or compute workload rather than a person. It provides credentials to your applications for authentication to Google Cloud APIs and authorization to access Google Cloud resources. You have the options to use the Identity and Access Management module to create a service account, and that's a good subject for another video, or use the default service account available that has basic editor role configured. Access scopes determine the level of access for requests made through the Google Cloud command line interface and client libraries in use by your application on the instance. As a result, access scopes potentially further limit access to API methods when authenticating through auth. And auth is basically an open standard that provides a way to get access to protected data from an application in a safer and more secure way rather than asking users to log in with passwords. So here you're provided with three options. Go with the default for limited access. Choose full access for unlimited access to the cloud platform. or set access levels for each API. The best practice though, when dealing with these two options, is to set full cloud platform access scope on the instance, then control the service account's access using IAM roles. Now, by default, all incoming traffic from outside the network or the virtual private cloud hosting this VM is blocked. You will need to select the type of network traffic you want to allow, and you're provided with two options for that: HTTP or HTTPS, or both. But for this demo, the instance does not need internet access, so I'm going to uncheck both options. So at this point, you should be good to create this VM, unless you have additional needs for networking, disks, security management, and sole tenancy. Under networking, you are provided with additional options to assign network tags which enable you to make firewall rules and routes. So basically, you can make a firewall rule applicable to this instance by using this tag as a source or target. Or you can make a network route applicable to this instance using this tag as well. Now, whenever you create a VM, Google Cloud creates an internal DNS name from the VM name, unless you specify a custom host name using this option. With this, you can specify any fully qualified DNS name. Custom host names are useful to maintain conventions or to support requirements for applications that expect a particular host name. You should note that though, you still need to create a corresponding DNS record in the appropriate zone, for example, by using Cloud DNS, that is Google's Cloud Domain Name Server. Next, enable IP forwarding if you want the instance to accept traffic for which it's not the target. Rather, forwarding allows the instance to help route packets to their target destinations. Next option lets you select a high bandwidth network configuration. You might have the need to be able to handle large distributed compute workloads, and you are provided two options for that. Select the Google Virtual NIC, which is meant to support higher network bandwidths of up to 50 to 100 gigs, and this mainly can be used for distributed workloads on VMs that have attached GPUs. But with this option, you should be aware of the OS compatible list. Please see the link for that in the description section. The VAT-IO option supports higher bandwidths as well, and on top of that, there is no OS support limitations, which basically means all available OS images in Compute Engine are compatible with this option. Now, further to this, if you're going to work with the Google Virtual NIC option, Compute Engine then lets you select a higher bandwidth Tier 1 configuration for certain general purpose and compute optimized virtual machine instances. And this includes the C2, C2D, N2, and N2D under compute optimized and general purpose, respectively. This option also requires the machine type to have 32 vCPUs and above. You should note that these are very expensive configurations and only go with these options when you really need a high bandwidth VM that can handle large distributed compute workloads with lots of heavy internode communication such as high performance computing, machine learning, and deep learning. I don't need any of these options, so I'm going to uncheck them. Now, by default, every virtual machine instance in a VPC network has a single network interface. However, you can configure an instance with multiple network interfaces. When using multiple interfaces from an instance, each instance must attach to a different VPC network. You can't attach multiple network interfaces to the same VPC network. This means all of the networks must exist before you create the instance. Next is the disk tab, and here you're provided with the options to add a completely new disk or attach an existing disk. Clicking on Add New Disk will side pop a window for you to set up the disk, and basically the parameters are similar to what we used to set up the boot disk. So you will need to provide a name and an optional description. You will need to specify the disk source with similar options as we saw earlier. Specify the disk type and size. Choose a snapshot schedule if one exists. Specify the encryption type or leave the default. And label the disk if you need to. Again, we saw all these options earlier while setting up the boot disk. The attachment mode allows you to get specific on whether the disk should be a read-only or read-write. As for the deletion rule and device name, we are familiar with this by now. So one thing to note is that the disk will be added once you create the new instance, but it will be unformatted. You will need to format the disk and then mount it on the instance to be able to use it. This link provides simple and straightforward steps on how you can achieve that. For cases where you need to attach an already existing disk, just make sure the desired disk already exists in the same hosting availability zone. As for the rest of the options, they are all the same as we saw earlier. Now, you might have the need for high security for your instance, and this is where Shielded VM and SSH comes in. Shielded VM comes with options for secure boot, VTPM, and integrity monitoring. Turning on secure boot helps protect your VM instances against boot level and kernel level malware and rootkits, while Virtual Trusted Platform module validates the VM's boot integrity. And integrity monitoring lets you monitor and verify the runtime boot integrity of your shielded VM instances. So this definitely requires VTM to be enabled. Turn on all these settings for the most secure configuration. Now, VM Access allows you to manage how users connect to the VM, and Compute Engine uses key-based SSH authentication to establish connections to all Linux virtual machine instances. This, however, is optional for Windows VMs, and we don't really need it for this demo. However, for cases where you really need SSH keys, especially when working with Linux VMs, Compute Engine will basically handle everything for you, from public and private key generation to the storage and maintenance and the authentication process. So you won't really need to do much. Plus, it's best to let Compute Engine handle this for you unless you have your own compliance reasons. Next is the Management tab that allows you to provide a detailed description of the VM. Here you can also enable deletion protection, which will prevent the instance from being accidentally deleted, especially useful for critical workloads. Reservations provide a very high level of assurance in obtaining capacity for Compute Engine zonal resources. The reservation prevents anyone else from using your reserved resources. Good thing to note is that reserved resources are charged at the same on-demand rates as running VMs on unreserved resources, although a reservation incurs charges for its reserved resources for as long as the reservation exists, regardless of whether or not its resources are being used. While consuming a reservation, a VM does not incur duplicate resources charges since the reservation is already built for the cost of the reserved resources. Here you're provided with three models. You can set the instance to use any available matching reservation, which is the default. What Compute Engine does with this option is assign the VM to any existing reservation that has the same properties as the VM you're creating. For example, same project, same zone, same machine type, CPU and memory, among other factors. This model is useful if you create and delete lots of VMs and you want to use the reservations whenever possible. The second model allows you to select a specific reservation. This model is useful, for example, when you want to hold a certain amount of capacity as backup for special events. And with the third model, you can explicitly avoid consuming resources from any reservation. Now, with this capability, you should know that for you to use either options 1 or 2, you need to create the reservations beforehand. Please see the link in the description section on how you can do that. Next, you're provided with the option to specify a startup script that will run when your instance boots up. Startup scripts can be used to install software and updates and to ensure that services probably required for your workload are running within the virtual machine. You will notice over here that this option is grayed out, as Compute Engine will allow you to pass the script directly only for Linux VMs. As for Windows VMs, you have to pass the script via specific metadata keys. The key name has to explicitly begin with the words Windows Startup Script. Then place your script in the value text box. For example, this script will install iaas on this VM. Though I don't need this for this demo, so I'm going to delete it. Next, you're provided with availability policies. And as for the provisioning model, you can stick with the normal on-demand model, which ensures the VM is up and running from the point you started to the point you stop or delete it. But maybe you have the need for a low-cost solution, and this is where spot instances come in. Spot VMs are available at much lower prices as a result of huge discounts compared to the on-demand price for standard VMs. However, Compute Engine might preempt spot VMs if it needs to reclaim those resources for other tasks. At this uncertain preemption time, Compute Engine either stops, which is the default, or deletes your spot VMs depending on your specified termination action for the spot VM. Spot VMs are basically excess Compute Engine capacity, so the availability varies with usage. Hence, you need to ensure that your workload is fault tolerant and can withstand the possible preemption. For this demo, I will stick with the standard option. On-host maintenance allows you to choose how you want Compute Engine to handle your VM when it performs periodic infrastructure maintenance. Compute Engine can either terminate the VM or migrate the VM to other hardware without downtime depending on your option at this point. And of course, for high availability, migrate is the best option. And to handle scenarios where your VM instance is terminated for non-user initiated reasons, let's say due to a maintenance event, a hardware failure, software failure, and so on, Compute Engine can automatically restart the VM or just leave it off. And definitely restart is the best option if you need high availability. Now, this next feature allows you to configure your VM to shut down automatically when you revoke the key that is helping to protect a persistent disk attached to the VM. You can revoke a key by either disabling it or deleting it. With this setting enabled, the VM shuts down within 3 hours of key revocation. In case you enable the key again, you can restart the VM with a attached disk that the key helps to protect. The VM does not automatically restart after you enable the key. Next is the sole tenancy section that lets you have exclusive access to a sole tenant node, which is a physical compute engine server that is dedicated to hosting only your project's VMs. Use sole tenant nodes to keep your VMs physically separated from VMs in other projects or to group your VMs together on the same host hardware. Although, provisioning a VM on a sole tenant node requires the following first. 1. Create a sole tenant node template which specifies uniform node properties. 2. Create a sole tenant node group using the template. 3. Create VMs and provision them on the sole tenant node group, which is what you do on this section. Please see the link in the description section on how to go about these steps. Now, node affinity labels are key value pairs assigned to nodes and are inherited from a node template. You create labels when you create the node template. The labels let you logically group nodes and node groups, and at this point they let you schedule your VM on a specific set of nodes or node groups. This is especially useful if you have the need to separate sensitive workloads from non-sensitive workloads. You specify affinity using this format. If you want the VM to be scheduled in the node group labeled dev, you can also specify non-affinity using this format to prevent the VM from being scheduled in the node group labeled prod. You also provided with the option to browse for the node groups existing in your projects in case you don't have the labels of head. CPU overcommit on sole tenant nodes let you schedule instances that can share their spare CPU cycles with each other. This feature is especially valuable for workloads that are underutilized but might experience relatively uncorrelated bursts. It can help you reduce per VM cost by spreading the cost of a sole tenant node across more VMs. It can also reduce per VM licensing costs when using per core licenses. Allow me to spend a little bit more time just to drive the point home on this. So at this point, you can specify the value for the minimum number of vCPUs that are allocated to this VM, but this only works on machine types with 4 vCPUs and above. So let's select one with those specs. And for this case, E2 standard 8 will do. Then enable overcommit. Now, the overcommit level represents the minimum number of underlying CPU threads, that is vCPUs, that are guaranteed to be available for this VM. This feature lets you provision VMs with different ratios of vCPU overcommit on a single tenant node. Lower values reduce capacity requirements at the potential expense of performance if correlated bursts occur. Determining an optimal value for the minimum number of vCPUs requires an understanding of your workload. So for this instance, if we leave the value for the minimum number of vCPUs equal to the number of vCPUs on this VM's machine type as it is right now, the VM's allowable overcommit ratio is 1.0. With an overcommit ratio of 1.0, all of the vCPUs will be accessible only to this VM, and there are no vCPUs resources available to be overcommitted to other VMs. But if we set the value for the minimum number of vCPUs to 4, then the VM's allowable overcommit ratio will be 2.0, meaning 4 of the vCPUs will be accessible only to this VM, and the other 4 vCPUs will be available to be overcommitted to other VMs. Before configuring the CPU overcommit levels of VMs, consider the criticality of your workload. Less critical workloads such as development and test workloads can potentially tolerate higher overcommit levels. More critical workloads such as production payment systems might not tolerate as much overcommit or any at all. Now, since I don't intend to use this feature, I'm going to uncheck this option and set my machine back to E2 medium. And with that, we are done with the VM setup. Click on equivalent command line to view this setup in command line form, which you can use on the Google Cloud Shell. Here you have the option to copy and save it in case you need to quickly redeploy similar instances in the future without using scripts, or run it immediately in Cloud Shell. You also have the option to get the REST equivalent that you can use to call the Compute Engine API directly from your code to deploy similar instances. So with all said and done, we can now deploy our VM. Click Create. This takes you to the instances page as Compute Engine spins up the VM. It took about 3 minutes for the VM to come up, so I paused the video until the VM was ready. So here you are provided with the options to RDP into the machine and additional options to set the password, download the RDP file, among other options. You also have the options to manage the VM like stopping, starting, deleting, viewing monitoring information and logs. Click on the VM's name to open up the management page. Here, you will find all the information that we've just set up, plus all the administrative capability you require for the VM. Now, before you can RDP into the VM, you need to set the Windows password. Click on Set Windows Password. Specify the desired username. I will call this one GCP VM user. Click Set, and you will be provided with an auto-generated password. Copy the password and keep it in a safe place. And now we are ready to RDP into the machine. Click on the RDP drop-down, then select Download the RDP file to get the file that facilitates the connection. Open the file and input your access credentials. Click OK. Click Yes. And there you go. Your machine is ready for use. And with this, ladies and gentlemen, we come to the conclusion of this video. Please share any thoughts or questions in the comment section, and don't forget to leave a like, subscribe to my channel, and click on the bell icon so that you're notified whenever I post similar videos. Bye and see you in the next one.